In this video, we'll be looking at using a Taylor polynomial to approximate the value of a function. Here in particular, we're interested in approximating cosine of 5 degrees correct to 5 decimal places. And we're going to use the fact that we know the Taylor series of cosine x to help us. Also recall that whenever we're working with cosine, sine functions, any of our trig functions, x is always measured in radians. So we know that this here is equal for all x measured in radians. So the first thing that we're going to need to do is convert this 5 degrees to the radian measure before I try to replace x with something. So notice that 5 degrees with a unit conversion, I know that I have 2 pi radians in 360 degrees here. So I'm going to have 5 pi over 180 or pi over 36 radians is what I'm actually trying to approximate. So we can say that cosine of pi over 36 is this infinite series with negative 1 to the n pi over 36 to the 2n over 2n factorial. And what we notice about the series representation that we have here is that this is an alternating series. So this question about approximating the value here at pi over 36 correct to 5 decimal places is a question that we could have had arise back when we first talked about alternating series and the alternating series estimation theorem. So if I want to approximate this correct to 5 decimal places, then what we want is for our error and absolute value to be less than or equal to 0.000001, okay, which is 1 over 10 to the 6th. Okay, so we have to figure out how many terms of this series do I need in order to get that error approximation. Okay, and then the sum of those terms would be a Taylor polynomial that I would be using to do the approximation. So we're going to use the alternating series estimation theorem, okay, which we recall says that the absolute value of our remainder is less than or equal to the n plus 1th term, or the n plus 1th magnitude of the next unused term. So what is bn plus 1 here? Well, bn plus 1 would be equal to pi over 36 to the 2 times n plus 1 all over 2 times n plus 1 factorial, and I want that to be less than or equal to 1 over 10 to the 6th. Okay, so with cross multiplying here, we know 1 over 10 to the 6th would be a million here. I'm trying to find the first time that 2n plus 2 factorial divided by pi over 36 to the 2n plus 2 is going to be bigger than this 1 million number. Okay, so easiest way to do this is just to start plugging in some values for n, try to find the smallest n where this right hand side is bigger than the left hand side. So I'm going to say right hand side here. What if I plug in n equals 1? Well, then I'll have 4 factorial here divided by pi over 36 to the 4th. Okay, it turns out that's equal to 413,829, so it's not big enough yet. But if we try n equals 2, let's see, I'll have 6 factorial all over pi over 36 to the 2 times 2 plus 2 to the 6th, okay, which turns out to be equal to this very large number of 1,630,227,688. So that's definitely big enough. So we're going to use the values up to n equals 2. So notice that this is the index we need to go up to. That's the same thing as the number of terms when n starts at 1, but since I have n starting at 0 here, I need to do cosine of pi over 36, which we know is cosine of our 5 degrees, is approximately equal to the sum from n equals 0 to 2 of negative 1 to the n pi over 36 to the 2n over 2n factorial. Okay, so that means we're looking at the following sum. If I plug in n equals 0 here, I have just 1. When I plug in n equals 1, we have minus pi over 36 squared over 2. And then if we plug in n equals 2, I'm going to have positive pi over 36 to the 4th all over 4 factorial. So notice that that is the, not the second here, but actually the 4th order, because we're going up to the 4th degree, the 4th order Taylor polynomial evaluated at pi over 36. So I've got cosine of pi over 36 is approximated by, okay, this Taylor polynomial, which means that's approximately my value of cosine of 5 degrees. And we wanted to actually find what that value is. So this value turns out to be, when I would add up 1 minus pi over 36 squared over 2 plus pi over 36 to the 4th over 4 factorial, is equal to 0.996. Oops. 0.996195. Okay, so let me clear up some of this. Okay, so this is the value here of the 4th order Taylor polynomial at pi over 36, but it is my approximation to cosine of pi over 36, or in other words, to cosine of 5 degrees, correct to the 5 decimal places that I needed for this problem. Okay, so we've seen how we can use both the alternating series estimation theorem and Taylor's inequality to help us get precise information about how accurate an estimate is for a particular x value or range of x values. We've also looked at how we can construct our Taylor polynomials. Let me know if you have any questions.